Thank you. So during the first part, we talked about classical error correction, and we saw a bunch of examples of small quantum codes. It's supposed to be like that. Yeah. And yeah, what I'm going to talk about today is more modern quantum codes. So topological codes. By more modern, I mean still 97. And quantum LDPC code, which is maybe the future of quantum error correction. And we saw that to define a quantum code, either we can pick a graph, the Tanner graph, and a set of qubits and checks, or we can build a matrix. And I just want to remind you that we need the check to commute. That's the only constraint we need. So we know how to define a quantum code. Now I'm going to talk about topological codes. So it's a broad term. Sometimes people talk about surface code, sometimes about homological codes. It's not really well defined. What I will mean by topological codes is this whole family built by Kitaev that led to the surface code. That is the one that people are considering today to build fault-tolerant quantum computer. And you will see that it's topological because there's a lot of topology. Okay, so first I'm going to talk about the code construction. And yeah, I named them homological code because the reason for the commutation of the checks, what makes everything work is homology. I'm not going to describe homology. You will have to trust me for that. But I just want to give you an intuition on how those things are built, and I'm not going to prove it. So the starting point is a collection of objects with different dimensions from 0 to d. So we can think of vertices, edges, faces, and so on. So it's a topological object. Like this is a graph. It's a graph with object of dimension 0, vertices, and 1, edges. And I'm going to add faces. So now I have square faces. I have objects with dimension 0, 1, and 2. Okay, I'm going to stick with 2 for now. And to simplify, I'm going to work on a torus. This is why it's called a toric code. It's the original construction of Kitaev. And that means that the blue side on top is identified with the bottom side. And the left and right side are glued together as well. So it's a torus. And now, what do we have in an object like that, in a homological complex? We have boundary maps. The boundary allows you to move from dimension I to dimension I minus 1. So for instance, what do you think is the boundary of a face? Sorry? Edges, okay. So the boundary of this face is going to be the 4 incident edges. It's natural, it's the way we speak in English, right? So we can do the same thing with an edge. The boundary of an edge is the 2 vertices, the 2 endpoints. So the boundary goes down in dimension. And we have another map that's called the co-boundary. And it's the same thing, but going up. So what is the co-boundary of a vertex? Okay, 4 edges. So it's a dimension up, so dimension 1, and incident to this vertex. And the co-boundary of an edge, the 2 faces, exactly. So now we can move between dimensions. And now that we can do that, we can build Kitaev's codes. We place qubits on object with dimension I. And because I will need I minus 1 and I minus 2, I'm going to pick I equal 1 in this case. I'm going to pick the middle dimension. And I'm going to place, so my qubits are the white dots here, white circles. I'm going to place a check on each object with dimension I minus 1. So the dimension below, I put an X check. So the dimension below is vertices. So it looks like that. The co-boundary of a vertex give me a check. And for a Z check, I will do the same thing, but from dimension I plus 1. So on dimension 2, I will put Z checks. So Z check is acting on 4 qubits. And this whole manifold does not matter for the code. It's just used to build the code. Once it's built, I can build a Tanner graph by putting a square that connects to these 4 vertices. but the code itself does not depend on the manifold. The manifold is used to build the code. Okay, and the proposition is that those checks commute. It's because of homology. You can prove it by using the fact that the boundary of the boundary is trivial. And I'm not going to do it. And you can do that with any manifold. Yes?
On the previous slide, the x's should be on the dark circles, right?
The x's should be on the?
Yeah, it says dimension I-1, so dimension 0.
So I define x checks for each object with dimension 0. So here I have one object with dimension 0. I will associate a x check with this vertex, but it's acting on qubit. So I'm going to put it on the incident qubits. That's what I mean. So yeah, we have nothing on black vertices. They are here just to define just as an.
So the z check is a check for that square, not for.
The z check is associated with this face. Yeah.
Okay.
And for higher dimensional manifolds, still x's and z's, or?
So it's still going to be x and z's in this construction, but I'm going to do it now with the toric code. So again, qubit on dimension I, check on dimension below and above. So we can do that in 3D. Let's say we have a 3D cubic lattice. Then I can be 2 or 1, right? So let's say we put qubits on faces. So if we put qubit on faces, the qubit looks like that. There is 3 directions, but they all look like a face. And that's another qubit. And on the dimension below, so dimension 1, I select an edge, and I'm going to put x on all the incident qubits. So it's a co-boundary again. And I do the same thing with a z on dimension above. So from a cube, from a 3-dimensional cell, I define a z check. And this is a 3D toric code. And we can keep playing that with any manifold. This is Kitayev's construction. Now there is an issue is that people wanted to build that, but to build in a chip. And the chip is not a torus. So we would like to lay it out in a better way. And for that, we can use the same thing, but in a planar cellulation. So I drew it in a slightly different way. So last time I tried to draw that, it was incorrect. So I hope this one is correct. It's not the usual drawing, but it's just to make sure it fits exactly my previous definition. So we have a square cellulation. You see that there is faces. Some faces are cut. Basically, I rotated the lattice, and there is no more identification. It's not a torus, it's a plane. And I cut the top and the bottom. There is no more vertices on top and bottom. And now I'm going to define a code in the exact same way. And this is Bravik-Kitaev, and at the same time, Friedman-Meyer, who introduced this planar version. And the rotated version was optimized by Bombin and Martin Delgado. So we have qubits on edges, same thing. X check on vertices. And Z check on faces. It's exactly the same construction as in the torus. The only difference is that we chop the boundary out, and this is planar. And this is a code that everyone is trying to build now. There was 3 experiments building it in the past 2 years. And there is some specific boundary operators where if you take this vertex, the check is acting only on 2 qubits. So there is weight 2 operators on the side. And the Tanner graph, we only care about the graph in the end, the Tanner graph in the end. So it's this object for distance 3, distance 5. And sometimes people draw it like that. It's the same code.
So
okay.
From toric to planar, is it just an annoyance due to boundaries, or there's some more fundamental stuff?
Yeah, it's just a small difference. There is some technical difficulties, like you need to adjust the circuit, you need to adjust to make sure that you are not propagating errors in the wrong way, but it's just small technicalities. There is no clear difference. Another difference is that there is 2 logical qubits in the torus. There is only 1 in the plane, but it's minor differences.
So in condensed matter, people talk about different phases of matter, some of them related to toric code. So do these discussions have implications in the design of a quantum error correction code?
I mean, phases of matter are often for the thermodynamic limit, for the infinite system. So as soon as it's finite, we don't see it. And what we observe, at least in classical system, is that if you look at the Ising model on any square patch, you look at a finite size system, and you can prove that the boundary effects are negligible. So whether it's a torus or a plane should be very similar. There is some small differences in the threshold, but it's very minor. Yeah, I'm not aware of any serious differences. In terms of quantum phases, it's also the same object. The phases locally are the same. Yes?
These pictures give the sense that the best would be that all qubits have 4 direct neighbors. However, I've also seen papers from IBM where they talk about surface codes where each qubit has 3 direct neighbors. Do you have any comment on this?
Yeah, so IBM had an issue is that there was frequency collisions in the way they control their qubits. So they wanted to have a smaller degree. So they use not a surface code, but a variant of a color code, which is another topological code, similar. And they use a different way to make it fault tolerant, to make sure they preserve this degree 3, to make it easier to implement. But it's a similar flavor. And I'm not going to talk about color codes. But there is many variants of the surface code. Okay, yes?
So in the toric code, you have this very nice or easy way of getting the logical gates, right? As like kind of lines that go around your torus. So what's the equivalent of that for these rotated?
So here, a logical gate is going to go from one side to the other. So there is one horizontal and one vertical. So logical X is horizontal, logical Z is vertical, or the other way around. And in the torus, they wrap around the torus, so logical operator, and there is 2 in both directions.
Could you remind me how to read this diagram? Because I'm just on the surface, they are all on the vertices.
Sure. So this is my qubits. So this is d by d qubits. Here it's distant 5, so there is 5 by 5 qubits, my wide nodes. And those are my checks. So when I have a blue check, I measure x, 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 x. And a red check, I measure z, 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 z. All the other way around. I don't know.
How do I see that one's on the vertex, the other is on the face?
It does not matter. So from now on, we only care about this figure.
So although conceptually they live on dimension 0 and dimension 2, but operationally you actually don't see it.
Yeah, so I will say we work in 2 steps. First, we build the code, then we use it. The way we build the code is by using some mathematical object. It can be a manifold, it can be a graph, it can be, later we're going to use product of graphs. But after we forget about that. We only care about the Tanner graph that tells us how the qubits must be connected. And then we want to implement a circuit that does all these measurements. This is the list of measurements I need to implement, basically. So I don't care about the original manifold. Yes?
Just one question for clarification. If I take the right-hand picture and rotate it, then I see a dot and a blue field and the dot, and that is exactly your color, red and blue. So, I mean, if I rotate it by, then I have first a dot, and then I have a blue field, and then a dot and a blue field, and that corresponds to the red and blue colors in the middle.
Those and those? Yeah, so here there is 2 types of faces. And there is one type of face that is a blue check, one type of face that is a red check.
Okay.
Yes, and the qubits are the same. It's also 5 by 5 qubits. But this one, this guy, is this guy. And the 2 in the bottom are the 2 in the bottom here. This is the most popular representation. But you see that I will have to explain a different construction when it's actually the same construction with boundary. That's why I didn't want to talk about it. But yeah, if you look at the literature, you will see that.
I have a question.
Oh, yes, sorry.
So the X gates are used to detect bit flips, right?
The X gate are used to?
Detect bit flips. And the Z gates are used to detect phase errors. So
Yes.
how does, like, in this case, not all, like, not all the cubes have all the checks, right? The X and Z checks.
So they do. So if I take a qubit, X is detected by, say, blue, and Z is detected by red.
Oh, okay.
But all of them have at least one blue and one red.
So that's why the alternative representation is the most common one, because all the qubits, you get both the checks and all the qubits.
I'm sorry?
Is that why the alternative representation is the most common one, because you get both the checks on all the qubits?
I mean, we need that. Otherwise, there will be one qubit in this grid that is not protected. So we need that. Forget about this picture. It's just a picture. I just want you to keep in mind that if you look at papers, you will see that. But it's the same object. I'm not going to use that at all. It's defined from that. And you're right. What you were saying is that, just in case people didn't hear, we need to make sure there is a blue square and a red square next to each qubit. And if my picture is correct, it should be the case.
What's the distance of this code?
So distance 3, distance 5. When you have a 5 by 5 grid, you get distance 5. Okay, let's try.
You represent a single logical qubit, right?
It's only a single logical qubit. So you see that it's expensive. And instead of that, in practice, you need distance 30. I mean, in practice.
So how did topological qubits improve upon what we did yesterday?
I haven't talked about topological qubits. This is for
Sorry, not qubits, topological codes.
So you see, I can tune my distance. Before I gave you examples with distance 3. I think I gave you only examples with distance 3. Here, I can go from distance 3 to 5, 5 to 7. I just increase the size of my grid.
Oh, so it's a lot easier to find the configurations compared to yesterday, where you said that it was very hard to find the optimal configuration.
So the problem of those small codes is that I need to concatenate. I need to encode, and if I want a better logical error rate, I need to re-encode and re-encode and re-encode until I reach the target I need for a logical error rate. So you give me an algorithm, you tell me I want a noise rate of 10 to the minus 10. Then I will find an encoding that gives you this noise rate. And if I do it with small code, I need to reconcatenate. If I do it with the surface code, I just need to increase the size of my lattice. So it's more flexible, and it can end up being cheaper.
And in practice, nobody uses Steam, I don't know how you say it, or Steam codes, the ones that you did yesterday.
I'm going to get back to that at the very end.
Okay.
Yeah.
Sorry, one more question. Is there an easy way to see why this has distance 3 and 5?
There is no easy way.
There's some intuition why it's...
I'm gonna get back to that.
And where does the magical number t equals to 30 is needed in practice?
Where does it come from? Yeah. If you do resource estimate for short algorithm, you need distance 27 for 2000 bits. That's the Google paper I mentioned at the very beginning. So 30 is a rough order of magnitude. Yes?
Just what's the overall scaling for this? So let's say I want to correct M errors. What size surface code do I need?
So I'm going to get back to that. I haven't told you again how we correct errors. I just told you how to define the code. So, okay, let's try to move on. And if I haven't answered your question about the surface code at the end, we can get back to that. So first, we need to measure the circuit, the syndrome extraction circuit. We need to measure those squares. And we saw one way to measure. It's to measure the check one at a time. We use one ancilla. We measure all the checks. And then we do the same thing again until we see the same syndrome twice so that we can trust the syndrome. So let's try to do that. Let's say we measure sequentially, and we repeat. So do you think it's a good idea? Do you think it's going to work? It worked before. So maybe it's going to work. So let's try it. So there is, let's say we have distance 30, which is what we may need in practice. So we have 899 checks. So yesterday we were repeating the measurement of 4 checks 4 times. Now we have 899 of them. In the meantime, each of them will cost you 4 C0 plus 1 preparation plus 1 measurement. So it's 6 times steps. So it's 5,000 times steps. So by the time you finish your circuit, there is 5,000 rounds of noise. Now you have 5,000 times more noise to correct, and you're in trouble. So we cannot do that. Let's try instead to measure all the checks simultaneously. And that's where the surface code is good. You see that it's planar, they are very local, so maybe we can measure all these checks simultaneously. And there is a circuit to do that. I'm going to show you the circuit for distance 3. So I have a grid of 3 by 3 qubits. And the circuit I'm going to use is the same as yesterday. We prepare a C0 and we do control X, control X, control X, control X. And for the Z checks, we do the same thing by replacing X by Z. And what's happening is that if there is a Z error here on my input qubit, it's going to remain a Z error at the end, but it's going to be propagating through the C0 and changing the measurement outcome. So I'm going to detect it as a flip.
Does it matter whether you control on the ancilla go up or control on the system go down?
So if I flip it, it's going to measure Z instead of X. So it measures something different. Yeah. But some people prefer to flip it. Yeah, so you can do either using only C0 and your C0 are up and down, up on some faces and down in the other, or you can do control X and control Z. Yeah, it's just a question of preference. If you have a fixed hardware, you don't have the choice. You do what you have in hardware. So the circuit looks like that. I'm going to do it here. So we prepare a plus state everywhere. We implement our control NOT or control Z everywhere, and we implement them in a specific order so that in 4 rounds, we can implement all the C0s simultaneously. And then we measure the ancillas, and we are done. And it happens that we can do that in a way that's going to spread error in a way that is not reducing the distance. So the fault will spread through the C0. If you have a fault here, it can spread through the C0 from the ancilla to this qubit, but not in a bad way. So this circuit was designed carefully to ensure that. Yes?
So naive question. Is the ancilla qubit a physical qubit or a logical?
Yeah, it's a physical qubit too. So in your grid of qubits, in your hardware, you need to have a square grid with extra physical qubit in the middle of the faces. It's still a square grid, but you need twice as many qubits. OK, now I want to give you an intuition on how we make it fault tolerant, because we saw how to measure the syndrome once. And like in Shor, we are going to measure the syndrome multiple times. We're going to use the same idea. So we are going to measure it D times this time. We were measuring it 4 times to correct one fault. To correct more than one fault, we need to measure many times. So, and we're going to have a graph like that in space-time, where the first time we measure, we get some graph. Oops. This thing is. So this is 3 rounds of measurements. Time goes up, and if we have an error on some qubit, we are going to detect it as. So those edges represent an error, and the endpoint represent what we detect. It represents our checks. I'm going to get back to the exact way we correct errors, and we see them like that. But what I want to say is that this vertical error is flipping a measurement outcome, and it can be interpreted as a Pauli error in a 3D surface code. So working with repeated measurement, 2D plus repeated measurement, is the same thing as correcting Pauli errors in 3D. We don't need to care about circuit fault. We can just move to a higher dimension, which is very common in physics. It's 2 plus 1D, it's 3D. So it works here, and the same algorithm can be used to correct errors in 2D or 3D. But I haven't told you yet which algorithm. So that's what I want to tell you now. So how do we decode? So I'm going to talk about decoders. So there is many decoders for surface code. It's a very trendy topic. The first one is from 2001, and that's one list of some techniques that were used for decoding. There is many, many different decoders. based on pretty much any kind of algorithm you can think of. They all have advantages. Yes?
I'm sorry, it's in the previous slide. Yeah, so in this, you're no longer repeating measurements like you did with Shore's method.
So I repeat my whole syndrome extraction circuit, this whole thing. Here, we have distance 3, so I'm going to do this same circuit 3 times on all the plaquettes.
So why are we doing it 3 times? Didn't you say that we can't repeat measurements in surface codes?
We do it 3 times because the first time we cannot trust the measurement outcome. It's not sure, it's similar. We repeat as well. It's not exactly sure scheme. Kind of parallel, sure, but it's exploiting the structure of the code itself. Sure will require more repetition, not D, but actually D squared. So it's better than sure because the code has a specific structure that we can exploit. It's hard to understand why D, but maybe when we talk about decoders, you're going to see that D makes sense. If you think that we need to move to a 3D surface code. I haven't justified it yet. So we need to correct a code. And I'm going to describe 2 decoders, the minimum weight perfect matching, which is based on matching, and the union find decoder, which is based on union find data structure. So first, the decoding problem. We have our Tanner graph. We saw that we have qubits with errors on qubits on those white circles. And we have some checks where we detect errors. We detect syndrome bits 0 or 1. The first thing we're going to do is that we're going to look only at the blue checks. And we can correct red and blue separately. We can correct X and Z separately. We're going to use the same algorithm twice. Now, when I have my blue checks, what's happening is that if there is an error Z, it's detected on the 2 endpoints. It's detected on the incident checks, right? It's what we saw yesterday. So I'm gonna draw it in red for a non-trivial value for a check. And another example is here. If you have a chain of error, Z, 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 this check does not detect anything anymore because it's detecting twice Z. It's anti-commuting twice, so it commutes. So the detection cancels out. We detect just an odd number of incident errors.
But you don't know if it's this path or the other path, right?
I'm sorry?
You don't know if that, I mean, if there's just one error and you know the 2 endpoints, you know exactly which edge it is. But in that case, there could be some other path that has the 2 ends, right?
So that's true. If the information you have is only the red check and you want to correct, and that's what we're going to try to do, we don't know if this is this path or this path of error. In this case, we don't know if this is this path or this path. There is many other paths. So we need to figure out which one we use to correct. And the only thing to remember is that when we have a chain of error, we detect the endpoint. So we detect the endpoint of chains. And now there is 2 types of errors. We saw that there is some errors that we don't care about because by definition, they stabilize the code. They are the stabilizers. So if my error is exactly a check, it does nothing to the code. I don't need to correct it. And if my error is a logical operator, if it's not a check, then I lose. I cannot correct it. So I'm going to review what are those checks. The checks are, they come from the product of Z here, right? So if I have 2 faces, that the product of the 2 corresponding checks inside those faces that I removed, give me a loop here, which is a stabilizer. So this thing, all the loops are trivial. They do nothing to my code space. They fix the code space by definition. And another one, it's a loop it's a path that's connecting the boundary to itself. It's basically a loop, but because I cut the boundary to make it planar, the loop is not closed anymore, but it's basically a loop. So those have no effect. They are trivial. Those that are non-trivial, that are problematic, is when they connect opposite sides, like this one. This is a logical operator. So how do I know that it's distance 5? It's because the smallest way, the shortest way to connect 2 opposite sides is 5. Now I can see the distance. The distance is the minimum weight of a undetectable error that is not trivial. Okay, so now the goal is to find a correction, and that after correction, what remains is a set of loop. It's a set of trivial errors. Let's do the matching. So you have some error configuration in red that you don't see, the red edges. You want to recover them, and you see the red checks. So you see 4 syndrome bits here that are non-trivial, A, B, C, D. And what you're going to do is that you're going to build a graph that I will call the distance graph. Inside this graph, you have one vertex for each highlighted checks. And the distance, so you connect all of them. It's a complete graph. And the distance between the 2 vertices is put as a weight on the edge. So the distance between A and B is 1. And the distance between C and D is 2. So C and D are here. Now we are going to work in this graph, and we are going to do a minimum matching in this graph. So the minimum matching here is 2 plus 1, it's 3. You can check the other possible matching. There is no lower weight. And based on this matching, we are going to build a correction. So my correction will connect A and D. So A and D is this path, and connect B and C here. I'm going to apply this correction to my qubit, and the question is, did it work? So let's look at the residual error after correction. There is my initial error plus my correction, and they form a loop. They cancel out, so the correction works. This is how the minimum weight matching decoder works. This is a bad way to implement it. It's very expensive if you do it like that, but there is more recent way. A lot of work by Fowler and more recent work by Higot and Gibney that get you down to n square complexity. Okay, now let's move to another decoder.
What's the complexity of the trivial way?
This one. So this one is it should be n cube.
N is
So n here is the volume of everything you decode. So you need to decode a d by d grid and d rounds. So it's d cube. It's d cube to the 5. So the complexity of this one is n5. So in the end, you end up with d to the 15 in complexity. That's why it's very slow.
okay. And the new thing is
And this one is a quadratic complexity in the volume, which is still d to the 6. The volume you need to decode is you have a grid of d by d qubits, and you have d time steps. So you do have a cube of d by d outcome bits that you need to match.
Where does the 5 come from?
The 5s come from the complexity of matching. So even if you use Blossom's algorithm, which is like Blossom 5, the fastest perfect matching algorithm, the complexity is, it should be number of vertices squared times number of vertices squared times number of edges. The number of edges in the complete graph is square. So it should give you d to the 5 if I said it right.
So this sort of reduction d to the 15 to d to the 6, which is the state of the art.
D to the 6 is state of the art. It's from this year for the matching. And it's worst case complexity. Yes?
I have a naive question. I'm assuming a classical computer is doing the decoding.
Yes, the decoding algorithm is done by a classical computer. And
Is there some intuition why the x and the y go up in degree and one below as being one computing some sort of motor integral and the other one just checking that the loop is closed, or like one is a total phase is 0, or its total phase is 1, and then the other one is that you've actually done enough flips so that you come back to the same one.
I'm not sure. Are you thinking of like a relation with electrodynamic or electromagnetism or something like that? So originally this thing, the surface code come from models come Levin-Wen model. So maybe it's related to that, and there is a lot of work on gauge theory, like electromagnetism, that has this kind of flavor. I don't know if it applies there. I don't know if this is what you have in mind.
Leavenworth, it came after toric code, right?
It came after. I think there is some previous idea that were very related. Maybe it's not Levin-Wen.
No, I think toric code was the first. Leavenworth came 6 years later.
There are models at least that are very related, and,
So
and electromagnetism has a similar flavor.
toric code is seen as a special point of a Z2 gauge theory, which goes back to the 80s. So,
Okay. Yeah, but I don't know.
So there is some idea about how fluxes in both loops.
Okay. Okay, so now I'm going to talk about another decoder, which goes from d to the 6 to almost d cubed in worst case complexity. And it's our work with Naomi Nickerson from a few years ago. So the idea is to say that if you see those red checks, you have some information. You know that in the neighborhood of this check, there is at least one Z. One of the 4 qubits contains a Z. So we're going to try to do a local correction using this local information. So I'm going to grow clusters, and I'm going to grow the smallest cluster first, but I know that for sure, one of the incident 4 qubits must contain an error. So I'm going to do that, and I'm going to keep growing the smallest cluster. And at some point, some clusters meet. When they meet, I'm going to check if I can find a correction inside the cluster. And now it's much easier because it's correcting inside a small cluster, and I can find any correction. So we can do that in linear time. And here in this case, to check if there is a correction that exists, I just need to count the parity. If there is 2 syndrome bits, there is a path that connects them. I don't even need to find it. I can just store 1 bit. And I stop growing this cluster. I keep it there, but I will stop growing it. And I keep growing the other invalid clusters until they meet. There is 2 syndrome bits inside. It's correctable. So I stop there. And then I correct those clusters independently. And I can correct them in linear time because I know that the error must be inside this cluster. And if we implement that in a careful way using a union-find data structure, which gives us the name, we can get a complexity n alpha of n, where alpha is the inverse Ackermann function. So this thing, if your number of qubits is smaller than the number of atoms in the universe, it's at most 5. So it's a very slowly growing function. So basically, it's a constant. Yes?
But the number of gates that you need to apply is now dramatically bigger, right? So I would...
The number of gates? So here I don't apply gates. It's purely classical.
Okay. I thought when you marked them red, that's where we're going to apply Z gates.
Oh, this is what the classical algorithm does. So my quantum circuit does the same thing. It's giving me all those syndrome bits. It's giving me a grid of syndrome bits, and I see some red vertices that I want to match. But before I was building a matching graph, a distance graph, in which I do a perfect matching. Perfect matching is expensive. And this distance graph is a complete graph, so it's a big graph. Here, I don't build any graph. I work in the native graph, which is planar, low degree, so things are going to go fast. But this is purely classical processing, yes. I think there was another question.
Yes. Now you combine these two, but how do you know where to start?
So
I mean, you could have also combined these upper ones and then try to do them first, right?
I mean, I did it because they were closer. That's why they got combined together. I didn't choose. Nature chose. Yeah. So the summary is that you get an algorithm that has almost linear complexity, which is better for worst case complexity. And there is a price to pay that it's reducing the threshold a little bit. But it seems that the threshold is not reducing too much, so there might be a regime where this trade-off is advantageous. Yes?
So when you're growing the cluster, can you bound the size of the cluster? Because if you have a very large circuit, it will have to build.
So you can, do you want to bound it in the algorithm?
Yeah,
So you can bound it, but you don't want to. If you bound it, you may degrade the performance of the decoder and not use fully the performance of the code. It doesn't matter if the cluster is big. If the cluster is big, it's easier because the decoder will fail, and the decoder fails sometimes. All decoder fails. Ideally, you want to make it fail with low probability of the order of 10 to the minus 10. And it does achieve that. It does achieve the full distance. So if you have less than d minus 1 over 2 errors, this decoder will work. Both decoder will work.
So why the quality of the decoder reduces the threshold?
Because even though it achieves the full distance, both have the same scaling. One of them is a constant time better because there is some configuration that we do not correct well here. The previous one will give you a minimum weight correction. This one will give you a correction, and which is not guaranteed to be minimum weight.
So the idea is that for complicated codes, none of the decoder corrects everything.
None of the decoder correct everything, yes. Even the previous decoder is not optimal. It's not a maximum likelihood decoder.
So why does the weight matter?
Sorry?
Why does the weight matter?
What is the weight metric?
I mean, why do you find the minimum weight? Like, why is it beneficial to?
So it comes from the noise model. We assume that errors on qubits are independent. So finding the most likely error is the one that has minimum weight. If you know that there is a single qubit error with probability 10 to the minus 3, the most likely is that there is a small number of errors because P is very small. So we look for the smallest configuration.
Yeah, but you may be correcting with some other matching, right? And you may still be able to correct the error because you are resolving a lot of some loops, right? Like, trivial.
Oh yeah. I'm not saying it doesn't work not to choose the minimum weight. In general, you should not choose the minimum weight, but that's a trade-off. It's easy to implement, and in the same time, it gives you a good performance. The best algorithm is actually based on tensor network contraction. It's Bravi and collaborators. The issue is that contracting this tensor network, even though the complexity is n squared, the constant can be very big. So it's a trade-off. You do what you can with polynomial time algorithm, with fast algorithms.
So in this case, the fact that you're forming clusters, doesn't that inhibit rings that you can find? And that would make...
Sorry.
So in this case, you're finding clusters and you're trying to correct within each cluster.
Yeah.
Well, just looking at it, visually, you could form a ring here, right? In this case, because there's core. So isn't that preventing you from forming rings that would remove the need to decode?
I can form. I'm not sure I see exactly what you have in mind. I can form a ring.
Yeah, maybe I understand. Maybe like my definition, understanding of a ring is incorrect.
A ring should be formed.
Wouldn't those 4 red dots go and form a ring in a complete graph if you don't form the clusters?
Yeah, I'm not sure exactly what you have in mind, but I mean, this is just an example to give you the intuition. Yeah, we can check a bit more about that. Yeah, I mean, there is many different algorithms. Some of them are faster. Some of them give you a better performance. You will have to choose depending on what you have in your hardware, how fast your qubits are, how fast you need the correction to be. Yeah. And there is some fast implementation you can play with. So there is pi matching and Fusion Blossom that both implement the minimum weight matching. And there is even some hardware implementation. People try to make it as fast as possible. There is a lookup table decoder by Google. And there is a union find decoder that comes from Yale, and a union find decoder based on implemented on FPGA from 2 days ago. They mentioned it earlier, but the paper is very new. The paper is just out, so I cannot comment on that. It's a variant of a union find decoder from Riverlane. So now, just to summarize surface codes, this is the kind of surface code we need for short algorithm. It's distance 25. We need even a bit bigger than that. It brings you from 10 to the minus 3 to 10 to the minus 12. So your logical qubits are very good. They can run large algorithms. And the advantage is that it has a high noise threshold. So you can tolerate up to 1% of noise. And we like to work 1 order of magnitude below threshold. And it can be implemented locally. You saw that the circuit is doing only local gates, which is what we can do with many hardware today. And the issue is that it's really expensive. This is 1 logical qubit and 1,200 physical qubits. So we want to do something a bit better. And that's why I want to talk about quantum LDPC codes. So first, I'm going to talk about code constructions. And I'm going to focus on one example for now. And after this section, if we have time, we can talk about a more modern construction, a breakthrough from last year. And that's even more fun geometrically. So this one is based on a product of 2 graphs. So we take 2 Tanner graphs. We have checks and bits. It's a bipartite graph or a classical code. 1 vertical, 1 horizontal. And we're going to take their Cartesian product. So the Cartesian product has 4 types of vertices. I'm going to call them circle, circle. And we're going to place a qubit on each circle, circle. So those are 9 qubits. We're going to place a qubit on each square, square. And we're going to place a check, an X check on the square circle. And the check looks like that. So horizontally, I take the edges of the horizontal graph, and I take a copy of this one to define my X. Vertically, I do the same thing. Vertically, this square is connected to two bits on top. I use the same connection. Oh, sorry. This square is connected to 1, 2. Is this correct? OK. So the figure is correct. And that gives us a weight 3 check. And I will define the Z check from the circle square. So to define a Z check, I do the same thing. I start with 1 circle square. Vertically, I look at the vertical edges corresponding to this bit. I get 1 that connects here. And horizontally, I have 3 horizontal edges that give me 3Z. And now you can see that they commute. Those 2, when they overlap, they will overlap in 2 directions because of this square in the structure. So the product structure makes it natural for them to commute. This is the hypergraph product construction. It's Tillich and Zemmour. And it was the first family of codes that encode k logical qubit into n physical qubit, where k proportional with n, and with a square root of n distance. Before that, we could only have log n distance if we have constant encoding rate. So now, again, keep in mind that this is just to build the code. The qubits are not necessarily going to be placed like that anywhere. It's just an algebraic object to build the code. Before, we were using manifold. Here, we are using a product of 2 graphs. Now, what is n? What is the number of physical qubits? Yes?
Did they have a geometric intuition for doing this monster?
The geometric intuition is the toric code. So if you take the graphs that are repetition codes, so the Tanner graphs are a line and a line, you will get the toric code.
Oh, it's the toric. Okay.
The product of 2 lines will be a square grid, and it gives you the torus.
But with different conditions on the
yes.
boundary, right? Okay.
Yeah. Yes.
Why is it not squared? Like why do we have more X checks than Z checks? Why is the vertical bigger than the horizontal?
Those 2 graphs, why are they different?
Yeah.
They can be anything. I can take any pair of graphs. They don't have to be the same. I haven't told you why I built that. I just told you this is the definition. Now I will tell you later what I put in these 2 graphs. But we can do it with any graph. That's the point. That's always going to work. Now you have to choose the right one. That's true. I chose those just to have a small example. So now, just to make sure we are clear on the definition, what is n? What is the number of physical qubits? Yeah, I heard 11. So there is qubits here, circle, circle, and square, square. So there is 9 here and 2 here. 11, okay. What is the first generator? So the first, let's say it's this one. And let's say I call that 1, 2, 3, 4, 5, 6, and so on. So there is 1 qubit on 4. So it's going to be III, XII, XII, and XI. Okay? So I can define my stabilizer matrix from that. Okay, now let's see how we choose those graphs. So to choose those two graphs, those two input graphs, we're going to take large graphs, and we're going to take 4 S bits with degree 3, 3 S checks with degree 4, and we are going to connect them randomly. So I take bits, I take checks, I put edges to preserve the degree in a random way, and we get a hypergraph product code with 25 S square physical qubits, with S square logical qubits. So it's pretty nice. It's 1/25, the ratio, and it doesn't change. It's not just 1, like in the toric code. And the check degree, or the generator degree, is 7. So before we are measuring only weight 4 checks. Here we measure weight 7. And the qubit degree is 6 or 8 instead of 4. So that's the price to pay. And in addition to that, they are not local, easy in 2D. We're going to talk about this issue later. But basically, the main point is that in the case of the surface code, you have 1 logical qubit. In the case of those LDPC code, you have n/25. And you have the same performance in terms of distance. And the number of ancilla qubit, I'm going to leave it a question mark because we're going to discuss it later. Okay. Now I want to talk about standard extraction circuit. We have our family of codes. They have constant rate, 1/25. That means 1/25 of my physical qubit is a logical qubit, which is very high compared to 1/1200 for the surface code.
What does ancilla mean? Not the uniform.
Oh, ancilla means the extra qubits I need to perform standard extraction. So with the surface code, I need an extra qubit in the middle of each phase. So I need half of my qubits to be ancilla qubits. So I have extra qubits that I need to run the code. And the issue with standard extraction is that, what do you think a typical LDPC code look like? Non-local, yeah? It's a random graph, so it looks like a mess like that. So it looks like an expander graph, if you want. Now, what do you think a typical quantum computer look like? Yeah, so our goal is to put this one inside this one. And you can imagine that it's not going to work well. It's going to be expensive. And I will not give you the proof, but I can give you a quick summary. So the first thing we tried is, can we do it? What is the cost of doing that? And we obtained a bound that proves that either the depth of the circuit is going to be large, and it's going to be square root of n, so it's going to be very large, or you are going to need n square ancilla qubits. So you have the choice between two cases that give you a code that doesn't work. And we designed optimal circuit for these two cases, and we simulated them, and even in simulation, we see that it doesn't work well. We lose more than 3 orders of magnitude in performance. Because we cannot embed this expander graph, this random graph, inside a 2D grid.
So what do you mean need in terms of how to define it?
I mean that we have a lower bound that gives us the total number of qubits needed as a function of the code distance. So if I remember correctly, the bound we get is something like that. Some constant. So the depth of the circuit is going to be some constant times n over a square root of the total number of qubits. So now, if you want this depth to be constant, in the surface code it's 6. So if you want to be less than 10, you are going to need this to be proportional with n. So the total number of qubits will have to be n squared. That means you need so many ancilla that even if you started with a rate n over 25, 1 over 25, you have so many ancilla qubits that it kills your rate. And that's what I mean. This bound gives us the two cases.
So naively, you need like a 4-dimensional thing, right? Minimally to get like a nice.
I can try to build a high-dimensional hardware, a 4-dimensional hardware, but it's harder. I could try to embed, yeah. No, so in any dimension, actually, we have a bound where this exponent is going to change. So the depth of the circuit is still not going to be bounded. It cannot be bounded in any finite dimension. And numerically, we also check that we get poor performance. So what we suggested, seeing that, is to look at long-range connections. We need to add something. So we added long-range connection, and we proposed a layer based on layout based on a few planar layers of long-range gates. That's what I'm going to discuss now. And with this layout, we can outperform surface code. And recently, there was some result of IBM from last month that improved even further this construction.
Is 2D hardware with a long-range connection, is it a scalable thing? I mean, you can do up to a point.
So it's hard to answer because I'm not aware of a single long-range gate today. So we need to build it. The goal of this work is also to motivate people. Once we know that we can beat the surface code if someone gives us the hardware, maybe physicists will be motivated to build it. I cannot build it. I don't understand the physics. But yeah, it's hard to build. It's challenging. It's not the end of the story. That's the main open question. Give us long-run connection. Oops. Okay, let's say you didn't see that.
2D local is dead.
2D local is not dead. That means we have to stick with the surface code. But if we want to implement LDPC codes, they don't beat the surface code because they are not fitting natively inside the hardware.
So is there a proof of that sort of statement? That, with locality,
I can give you the reference for this one. It's our paper here. It's the first one is giving you this bound. The argument is based on expansion. And yeah, we can discuss that if you're interested.
This is maybe like a West Coast perspective, but every time this comes up, the ion trap people will say, "Oh, we can connect anything."
I mean, so my feeling is that our bound actually applies to ion trap or neutral atoms, and the reason is that even though you can move your qubits, if you cannot move them instantaneously, you are implementing a circuit. So let's assume that time is discrete. You are moving your qubit one time step at a time in a discrete lattice, maybe very small but still discrete. And asymptotically, these bounds apply. And actually, the last paper of Cura, where they consider exactly the same scheme that we have in this paper with long-range connection, they do mention that asymptotically it doesn't work, but there is maybe a regime where for finite size, if they can move their atoms fast enough, it can work. We don't exclude that. It's an asymptotic bound, and it's worth exploring.
When you say move atoms, it's because you want
what?
For a neutral atom and ion trap. When you say move atoms, is it because you want to form these new connections?
So the claim is that if you don't have qubits that are fixed in your hardware, you can maybe move them next to each other, implement a long-range connection, and come back. My claim is that this is applying a permutation, which is a circuit, which is also subjected to the same bound.
So are long-range gates at all possible in superconducting architecture?
So I don't know, I'm not an experimentalist, but when I think of long range, the way I think of it is that you have 2 qubits, you are going to convert them into a photon, use optic fiber, and do a gate thanks to that, thanks to entanglement created with photons. But maybe it's because I don't know the physics that a photon in optic fiber seems like a good idea. I don't know. It looks like a long-range connection, no? I'm sure most people here know more than me about that. So. I should not comment.
I think there's also a notion of long-range entanglement, which I tried to understand a couple of years, but I don't. But it's probably even harder than what you're trying to do. So maybe there is something, but that could be equally complicated than
Yeah, I mean, yeah, and yeah, we're asking for a lot, but the goal is to motivate the research in that direction because now we know that we can beat surface codes. Yes?
Maybe I've confused myself now, but what do we actually mean by long-range interactions? Because even if you don't have to shuttle atoms around, right, does the finite speed of light also impose these same aspects?
So I'm going to discuss that now. I'm going to discuss what I mean by long range.
Oh, sorry. I guess I should probably speak up because I kind of do a little bit of hardware. There's been, like, for long-range connections, for a transmon, there's been an idea of a multimon. So you connect all of the JJs together, and but you can get like an all-to-all connectivity for transmon architecture. So like that's one way for JJs. And then for photons, you can do this thing called phantom interferometry, and that you can do non-local gates. So there's a paper out of the group that I'm currently in that was published in Nature Photonics where we demonstrated a non-local swap gate.
What group is that?
Professor Chiwei Wang. Yeah.
Okay, that's interesting. Can I ask you to jump in again after the slide so that I show you what kind of graph I want, so that you tell me if it's crazy? No, I'm serious. I would be curious to have your opinion because we don't need one long-range connection. We need many of them. Yeah, so let's say you didn't see what I was showing. What's the most naive way to draw your circuit? I'm gonna put the qubit on a circle, and I'm gonna connect what I need to connect. This is a graph with 100 vertices and degree 8. So it's about what we have, but instead of 100, we have thousands. So I'm not an experimentalist, but I don't want to build that.
So these are all the connections you want, right? There are no implied local connections beyond that, right? This is the complete graph that you care about.
So this is the kind of graph I care about, yes. My qubits are here, and by connection, I mean that I'm going to apply to a C0 from this gate to this gate. C0 or CZ. And if you can give me that, maybe for small codes, they can build that, but it's maybe not going to be very scalable. And our intuition was that if we have this kind of design, each crossing gate is going to introduce some noise. It's going to introduce correlated noise, which is bad for our code. So it's likely not going to work. And because of that, so we think of something like that. We apply a C0. There is a fault on this qubit. It's going to spread the fault here. But if in the same time you apply another C0, it's going to spread this fault to the other qubit and to a third qubit. And it's going to start spreading very quickly. And by nature of this graph, because it's an expander, it's going to spread to everything very quickly. So we want to avoid that. We want a small number of crossing gates and a short depth. And this is what we designed. And I'm going to give you the intuition with just the Tanner graph. So this is the Hamming code. How do we do that? We decompose it into two layers, one layer here and one layer in the bottom. So I moved one of the check up to make sure it fits well. I think this check moved up in this layer, but it's planar. And now I will have to implement C0 from these qubits in a way that is biplanar. So if we have degree 3, we have degree 4, we have two planar layers. In our case, we have degree 7, so we end up with 4 planar layers, sorry. And that's the performance we get. We have a logical error rate that decays very quickly. So Maxime, our intern, a few years ago did this simulation. It's non-trivial simulation. You have to simulate the circuit and generate these codes and select the right codes. And with circuit level simulation, that's what we get with LDPC code. You can probably not compare with surface code unless you know the numbers by heart. But the comparison is that the threshold is about twice lower. So it doesn't beat surface code in that sense. The number of physical qubits is 49 per logical qubit, including ancilla. So there is, instead of 1/25, it's 1/50. And for surface code, it's d square physical qubit. So it's 2d square, sorry. So as soon as you reach distance 5, So the overhead is more expensive. You can only use a distance 5 surface code, but you need 30. And the layout is 4 planar layers, and it looks like that. So there is many gates that are in one direction or in the other direction, and they can be decomposed into 4 planar layers. And to go down from 10 to the minus 4 to 10 to the minus 15, we need 13 million physical qubits with the surface code, or 900,000 physical qubits with these LDPC codes. So there's a 15x reduction. And now what I mean is that in these layers, we have thousands of long-range gates. This is the main issue, that we need hundreds of thousands of physical qubits and thousands of long-range gates. And we need to turn on many long-range gates in parallel. So we need to be able to implement a CNOT from this qubit to this qubit. So at this time, I believe we can be optimistic. Surface code, we can beat surface code, but we need this hardware, and we need a lot of qubits. And during the last months, IBM proposed this paper where they have a lot of improvements of this work. So the threshold goes from 0.3 to 0.8. They almost double the threshold. The number of planar layers goes down to 2, and the number of qubits goes down to 300. So now there is even more hope for LDPC codes. We still don't have those long-range connections. It's not exactly the same overhead, but it's still the same 15x improvement in qubit count compared to surface codes. So same improvement, yeah.
It still needs those long-range connections, right?
You still need those long-range, yes. Thank you.
Okay.
Yeah, so that's the main open question. And it's not a question maybe for any of you, or maybe for some of you only.
Sorry, this is maybe going back to a little bit previous slides, but the one graph you showed for the LDPC codes is like a random haphazard, right? I'm just curious, like, how do you mathematically construct your LDPC codes? Because your non-planar, that will depend on the structure of your LDPC code itself, right?
Yeah, so I take the construction that we saw before, where we take 2 random graphs, and we take the Cartesian product. So 2 random graphs,
So it's all random.
sparse degree.
But I mean, there are de-randomized versions of this kind of stuff, right? I mean, there are these ways of producing matchings that are performing as expanders, right? In fact, better Ramanujan.
So yes, and we actually don't only want expanders. There is a lot of properties that we want, because we also want the decoder to work. And we know that for the decoder to work, we want extra properties. So we generated those graphs randomly. Then we discarded the graphs that have a small girth. Then we ran simulation over thousands of codes to select the best one. And then we ran this circuit simulation. So Maxime did a lot of work to get those results.
But the kinds of things that you get from groups with property T and so on, I mean, the kind of classical constructions of expanders, they're not useful. I mean, they have some interesting symmetries, but
yeah, you can try that. But even classically, those classical expander codes are not the code we use in practice. Because the issue is that they have a very restricted set of parameters. The degrees must be tuned very carefully. The size of the graph is fixed by the size of the group you take, depend on PSL2, and it's not very flexible. If I take a random graph, it's very flexible. Yes?
No, go on.
So it's still the same 10 to the 15 accuracy?
So at 10 to the minus 15, you get 15x improvement, from what I remember. Yeah. So you use 15x fewer qubits compared to the surface code. When you want to reach...
Back to the previous slide, just to appreciate this thing.
Yeah.
Previously, you had this 900,000.
Yeah.
That's the qubit count to get to 10 to the minus 15 accuracy.
Yes.
And then you have this, I don't know whether this 900,000 is related.
Yeah, this is the same.
Yeah.
So it becomes 300.
Yeah, 300 also achieve 10 to the minus 15.
So yes, it's to achieve. Let me try to remember. So, no, maybe this one does not achieve 10 to the minus 15. Maybe it's at 10 to the minus 12, but it's the same 15x. Yeah, I took the comparison in terms of qubit count reduction. So we have 15x reduction in qubit count, and they have 15x qubit reduction in qubit count. Here, this one is a bit lower. I don't remember the exact logical error rate, but this is lower. And it also, it's not exactly comparable. I just want to say that there is a lot of... what I mean is that here we have all the qubits encoded in a single block, which has to be very large. Here they will have multiple blocks of 300 physical qubits, which is more convenient, easier to build. So that's one advantage. And with this size, they have an improvement over the surface code. I think their example is if you want to encode 12 logical qubits, either you use 12 surface codes, or you use one code with length 300, and the total cost is 15x more for surface code. It's a bit hard to compare because it's points that depend on different parameters. But I mentioned this one because it's an issue of our construction, that you need very large block lengths. We are still in the asymptotic regime. It's not anymore asymptotic. Yes?
I have a question. So this need of long range is something you proved or you observed?
This need of long range?
Yeah, is that something you proved that if you do it all locally it doesn't work, or is that simply you can, well, there, yes.
It's this bound that tells us that
So that also applies to all the multi-layer.
Yeah, multi-layer or not is independent. Yes.
Okay, so that always applies.
Yeah, it applies to anything that is implemented locally.
Okay. And these examples, they are found by some computer-added thingies? I mean, the 300, or are they? Did they write them down? I mean, how are these examples found?
Numerically. So it comes from a family of code introduced by Kovalev and Priatko a few years ago.
And then they search.
And numerically, they search for the right code, and they found one. They found a few of them. Yes?
So this is all done in the context of implementing a quantum memory. I'm curious, like, what the status of like a logical universal gate set is for these codes.
Yeah, I'm not going to mention that, and yeah, it's a quantum memory, so I don't have the answer. So you can guess that. I'm going to tell you I don't know.
Okay.
But there is some protocol that are encouraging. I think it's one place where there is a lot of work needed, implementing fault-tolerant logical gates. There is a kind of lattice surgery for LDPC code that is promising. I think it's a clean structure. I'm going to cite it at the end.
Do you still repeat the measurements? Like you do multiple rounds of measurements for the...
I'm also going to talk about that at the end. We can make them single shot. So in our case, we did only one round, and it's enough. It's fault tolerant in one round. So it's another advantage of LDPC codes. Okay. So now, am I done or do 1 minute? Okay, so I mean, it's a good bonus part. You will not have it. Okay, so what I will mention is just this breakthrough that so last year, 2 years ago, Panteleyev and Kalachev proved that we can build LDPC code that are good in the sense that they have a linear number of logical qubits and a linear distance. It's optimal, it's the best we can do, and it took 20 years to build that. And it's based on high-dimensional expander. So I'm going to go through my slide very quickly. You're going to see a bunch of figures. And I'm going to jump to my conclusion.
It looks like it would have been very interesting.
It's about high-dimensional expander, about those constructed by Deneural, Lubotsky, and collaborators.
Again, if there's interest from the audience, and if you could give another Zoom talk.
Sorry?
I mean, if there is interest from the audience.
Oh, I'm happy to talk. I'm here the whole week, so I'm happy to chat with anyone.
This week may be a little bit full, but then after that, during the off-workshop weeks, and if you can.
Yeah. Okay, we can talk about that.
Personally good.
Or probably even better.
So yeah, my conclusion is that with surface code, there is already surface code experiment from ETH, from China, and from Google. It's exciting, but the main issue is that we have a large overhead. LDPC codes are promising. They can reach a better overhead, but they need long-range connections. And there is a lot of promising results. So I'm adding things that I did not cite during the presentation. So Gottesman is the one who introduced first the idea of using LDPC for quantum computing with low overhead. This scheme is generalizing the lattice surgery. So we can do the logical gate with this scheme. And they are single shot, so they can be very fast. We don't need to repeat measurement. And we have another variant of LDPC code based on hyperbolic manifolds. Like KITAF, but on hyperbolic manifold, and you can get LDPC code like that, and good performance. And I also don't want to discard concatenation. It was very useful originally at the beginning of quantum error correction, in particular, the most popular proof of the threshold theorem. It's called AGP, Aliferis-Gottesman-Preskill. And it's based on concatenation to prove that we can do error correction in polylog cost. And more recently, I'm very excited about this paper that shows that we can concatenate in a way that gives us a constant overhead. So we can get the same overhead as LDPC. It will be good to have numerical result and to know exactly how it works in finite size, and if it works better than surface code. And that's the work of Quera recently, where they use the LDPC code we consider, the same construction. And well, they propose to use that, and they believe that in some regime, even though by moving atoms, they can implement the circuit in a way that is fast enough for finite size. Oh, sorry, this is the one. Those are the same, right? Okay, that's not what I wanted to put here. Okay. And yeah, more things that I didn't have time to talk about. There is a lot of work in error correction outside of what I talked about. And wow. I'm going to stop here. Thank you.